the YouTube, and then we can start.
Estamos ao vivo.
Okay. So, hello, good morning, good afternoon, everybody. It's a great pleasure to have here Rozema from University of Vienna. Just like to say a few words about. He did his PhD. He's from Canada. He did in Toronto, Einstein-Berg, right? And 2014. And then I heard of his papers at that time. At this time, we never met. And then he moved to Vienna as in the beginning working with Philip Walter, and he's permanent in University of Vienna and collaborator with two-qubit, and doing quantum optics, photonic applications automation. And now he's going to talk about this using nonlinear graphics. Very interesting topic. So then I again leave for accepting this invitation. Welcome. And I think you have 50 minutes, and then we will have 10 minutes for discussion.
Okay, sounds great. So you guys can already see my screen, right?
Yeah.
Okay, great. So yeah, thank you very much for the invite. It's a pleasure to talk about this stuff. I can't be there in person, but this time. Thank you very much for the introduction as well. As Paolo mentioned, today I'll be talking some of our work that's a little different. So since I've been starting this project for nonlinear effects in these interesting graphene systems, and the goal is to one day do quantum information experiments using these platforms. But before I get into that, I want to just say about stuff we do in Vienna in general. So this is our group's more well-known work, and this is around. So a big thing that we've been working on in Vienna for a long time is using spontaneous parametric down conversion to create entangled states of light. And we use this to demonstrate a variety of quantum information protocols, quantum foundations, and so on. More recently, the group has also started to diversify, and we've been looking at ND centers, and we just have really brand new. We've been renovating the labs to get this big quantum dot project off the ground, multi-photon entangled states using photons from quantum dots. Of course, when you make photons, you also need to detect the photons. It started as somewhat of a collaboration, but we still work fairly closely with this Californian company from the US, Photon Spot. We have commercial systems, but we're also working on a project with him to develop single photon detectors based on superconducting nanowires to detect photons at very long. So right now our target is looking at detecting photons at 3,000 nanometers, and you'll see kind of towards why we're interested in this. We also to look at manipulating single photons. So once you make photons, you want to do something fun with them. So we have from bulk optics to fibers to integrated platform. A lot of our work has focused on laser written wave, but we've also been starting to move towards integrated platforms where you can have looking at silicon-based technologies. And something that's kind of closer to my heart, and something I really is, once we have this big playground where we can make nice entangled states, manipulate the photons, we start doing, the real fun stuff, doing quantum information and quantum film with them. And this is really my background. So during my PhD, focused on quantum foundations experiments and so on. But I'm going to focus on something different. This is something that's fairly new for us. And I'm going to a theory paper that we put out, I get the date here, I guess it was last year, which we called Quantum Computing with Graphene Plasmons Details. And I'm going to try to focus more on the quantum information aspect of it and show you kind of what these sorts of gates require, then tell you how the graphene plasmonic platform seems to be a nice candidate for implementing these gates. So I'll try to focus more on the that's I think is more the background of the audience as well. And then I'm going to present our recent experimental work, which was just a few weeks ago accepted in Nature Nanotech, will appear soon. And this is really our first experimental effort to try to look at these effects. Just a caveat, everything in this paper is classical, so we're really just looking at characterizing the nonlinearities in this work. It really highlights the versatility of this platform. So, yeah, so just again, I'm going to start with just some simple motivation, then we'll go into the theory before getting into the experiments. So, what are a picture down here of one of our tables in Vienna? So this is a picture of our, this is a picture of our 6-photon source. So each of the around the nonlinear crystal. In this, it's a PPK-DP crystal in a sandwich geometry. But in general, very spontaneous parametric down conversion, where we pump some nonlinear laser beam and we start spontaneously generating photon pairs. So of course we know that this is a very weak process. Only something like 1 in 10 million photons are converted into a photon pair, but nonetheless we can make very high quality entangled states using this sort of technology. And what's also nice is we directly get entanglement right out of the source. So we can get pairs of photons that are entangled. So once we have 2 photons that are entangled, we want to start your larger quantum system. So if we take 2 pairs of entangled photons, ideally we'd like to take these, entangle them together to get a 4-photon entangled state. And to do that, we need, if we abstract it, we need a quantum logic gate to do this. So we need the state of one photon change the state of another photon. And this is what 2-qubit logic gates do. So most people know of the control not gate, where I've written out the truth table here. The first qubit state is 0, nothing happens, and qubit remains the same. However, if the first qubit is found in state 1, the state of the second qubit flips. So you see the 1-0 state goes to 1-1 and 1-1 goes to 1-0. And this is nice because we can use it to actually generate entanglement. So if we pull state where we put the first qubit in a superposition and the second qubit is in 0, after applying the control not gate, we're going to end up with an entangled state, 0, 0 plus neglected normalization here. But of course, the control not gate, useful gate. The controlled phase gate is another very, and its truth table looks a little bit, it doesn't look like kind of as much. You have, again, the same state where you have 0, 0 going to 0, 0, 0, 1 going to 1, 0, 1. And this state now, the 1-0 state also goes to 1-0, but what happens is when both qubits are in the state 1, we pick up a negative sign. So we get a phase applied when both qubits are in state 1. And this turns out to be equivalent to the controlled not gate. And we say that either of these gates together with a single qubit gate, a family of single qubit gates compose a universal gate set. But in this talk, I'm going to focus on on a less well-known gate, namely the root swap gate. So this gate here, it essentially, the way I think about it is it creates a superposition of the 2 input states having swapped and not swapped. So for the 0, 0 and the 1, 1 states, the gate doesn't do anything, but for the 0, 1 state set up with the superposition of 0, 1 and 1, 0. So the photons or the qubits are in a superposition of swapping and not swapping. So this is why it's kind of a root swap, why it's called a root swap gate. It's like halfway swap gate. And if you're interested, you can work out this identity, this little circuit identity. These 2 qubit gates here are the root swap gates. Sorry, my screen appears to be cut off. Let me just see if I can. I don't know. I don't know if there's anything I can do about this easily. Okay, yeah, just so I'll just be aware of that. So yeah, so anyways, there is a circuit identity. You can use 2 root swap gates to create a controlled NOT gate. So what do these gates typically look like? Well, most of these gates in photon are based on combining photons on linear optical elements. And we like to do this because this is easy. Linear optical elements are relatively inexpensive, and they're fairly straightforward to align, and they're kind of the heart angling gates. And what it comes down to is really the Hong-Mandel effect. So if we consider 2 photons incident on a 50-50 beam splitter, several different things can happen. We can have both photons. We can have a situation where both photons emerge in separate exit ports, or where both photons bunch into one port or the other port. And now you may know that if these 2 photons coming in are indistinguishable, if they're identical, we have interference, and the first term never happens. This is the kind of famous Hong-Mandel, the Hong-Mandel experiment, and this is the Hong-Mandel dip, where what we're doing is we're looking at the probability of both photons to exit as a function of the delay between the 2 photons. So we're literally just changing the time at which the 2 photons hit the beam splitter, and we see that when both photons hit the beam splitter at the same time, the coincidence rate drops to 0. And then what you can also show with these sorts of setups is if we take our beam splitter, and instead of having a beam splitter, we tune it off a little bit. So say we go to a 40-60 beam splitter, so handle interference partially goes away, so we can have events where the 2 photons exit in different ports. We pick up this negative sign. So this is a controlled phase gate where we have a 1-1 transforming into a negative 1-1. And this is indeed the case if I'm not going to go through that. We can use this to directly implement a controlled phase gate for specific values of the reflectance and transmission. And this works quite well, but it doesn't work all the time. So this comes at the cost of requiring post-selection. So now we don't have a gate all the time. For this particular gate, it only works 1 in 9 times. So 9 out of 10 times, the 2 photons are going to bunch, and we're going to have to throw away the result of that gate. I do just want to mention, though, that this is still a fairly versatile setup to create a 6-photon state where we have 3 single photon sources, and then we take 1 photon from this source and 1 photon from this source, interfere them on a beam splitter, and the 2 photons emerge in separate ports. We have generated entanglement between this source and that source. And we can do the same thing between these 2 sources. It works well, but this is nonetheless difficult to skip a way to make this deterministic, ideally. And if you have a nonlinear optics, this controlled phase gate may already look like some sort of nonlinear effect, where if we have 2 photons present, we pick up a phase, and this phase can be implemented with a strong Kerr nonlinearity. So if we have photons interacting in a nonlinear medium, where the state of 1 photon changes the refractive index enough that the second photon will, pick up a phase, you can use these sorts of effects to do these gates directly. And if we could do this strong nonlinearity, we wouldn't require post-selection anymore. This works. People have done this with great success. Challenges so far is that the strength of the nonlinearity that you require to implement these sorts of gates is huge, and you really need to go to like single atoms or atoms, which requires a lot of infrastructure. So it's kind of difficult to imagine taking an experiment that tables and integrating it down to a chip that's going to let us scale up our technology. So, and that's what we want to do here. We think that graphene provides a way forward that we can create your effects, but now with a very, very small footprint. So before getting into the graphene side of things, I'm going to focus on a way we can, just using a generic nonlinearity, the way we can take one of these gates, in particular the root swap, and try to make it deterministic. So remember, the root swap gate is this gate that takes the input states and creates a superposition of the input states swapping and not swapping. So if we now think about a beam splitter again, and we send a photon into a beam splitter, after the beam splitter, we have a state, this, a superposition of the photon being up here and down here, so the photon has either swapped or not swapped. And if we completely ignore Hong-Mandel interference, this wouldn't actually happen in the lab, but if we ignore Hong-Mandel interference, and now we send a photon in the upper, afterwards we get exactly the state we want. So a state where the photons have swapped and not swapped. So this is the root swap gate. Of course, it doesn't actually work with indistinguishable photons. And even if you make your photons distinguishable half of the time, because half of the time the two photons are going to exit in the same port, it's not going to give you the output that you want. So if we keep this gate in mind, we have a beam splitter, which is very close to implementing a universal quantum gate. So now how can we take this simple idea and turn it into something that works all the time? Well, to do that, we're going to use the Zeno effect. And this was an idea that was originally proposed by James Franzen back in the early 2000s. And I'll just review briefly the Zeno effect before getting back to it. So the Zeno effect, you may be aware of, is this idea that continuous observation keeps the quantum system in place. So kind of the prototypical example of this effect is if we consider an atom. So we have a two-level atom, which can either be in the ground state or the excited state. And we're going to, at time 0, we're going to kick our atom up into the excited state. And now if we don't do anything in the atom, we know that there's going to be some probability for that atom to emit a photon and decay into the ground state. So if we don't do anything, the system evolves from excited to ground state. But if at some time over here, we measure this system, there's a high probability that we're going to find the system in the excited state. And if we find the system in the excited state, quantum mechanics tells us that, well, now we've collapsed the system to the excited state. So we've essentially pushed the quantum system back up into the excited state. And now the photon or the atom can start the decay process over again. Of course, if we wait too long to measure it, if we wait till we're, say, somewhere over here to measure the photon, now there's a high probability that the photon is going. So we really need to do these measurements very quickly with respect to the decay time. But if we keep doing this, we can keep and we can essentially keep the atom in the excited state indefinitely. This is kind of the usual quantum Zeno effect. I do want to mention, though, that this effect rarely quantum, you can also think of classical systems that behave somewhat similarly. For example, Malice's law, which is a very well-known effect from classical optics, it's maybe a little different than the Zeno effect, but it has quite a few similarities. And I'm just going to roughly explain that. So imagine we have some linearly polarized light, say polarized along the V direction, and we have a polarizer oriented along the H direction. We know that if we send light to if we send light to this sort of a polarizer, it's not going to be transmitted. However, if we take our polarizer and we rotate it over here, now there is going to be some of this input light will be transmitted through that H polarizer, and the light that's transmitted will furthermore be polarized of that initial polarizer. So now we end up with the state over here. And now if we take another polarizer, we can orient it, say, again at some small angle to this new polarization state. And then the light will be rotated here. So the light that makes it through the polarizer. And then we can keep doing this process. and we can eventually end up with some of the light transmitted at H through this polarizer, even though this polarizer is completely orthogonal to the original input state. And if we do this, continuously enough, smoothly enough, we can actually get a situation, in the limit of an infinite number of polarizers where all of the light makes it through. So now we want to take these ideas and apply it to this simple root swap gate, this simple 50-50 beam splitter. We want to somehow measure whether or not the photons have swapped and use this to keep the photons in the right modes. And the first step is we need our 50-50 beam splitter and turn it into a continuous beam splitter. And we know how to do this. We can use something called a directional coupler, which is based off of evanescent coupling, to achieve a continuous swap. So what's happening here is, imagine that we have some photon, and that, say, these green wires here, or these gray wires, are optical modes. Say they're fiber optic, just fiber optic cables. And now we bring those two modes close at the evanescent field. That we know that this photon propagating in this fiber has some field which extends outside of the actual fiber. And if we bring the fibers now close enough such that this fiber extends into the field of this fiber, the photon can couple from this fiber into that fiber. And the probability that the photon couples depends on how close you bring them and how long they're in close contact. And we can find a length at which there's a perfect probability that the photon, that there's a probability of 1 that the photon swaps and ends up in this lower mode. And then if we take that interaction length and we just divide it by 2, now there's a probability. Now we can directly implement a 50-50 beam splitter where the photon from this mode will end up in a superposition of these two modes. So now we have a continuous. Now we have a continuous swap process, and the next step is to take this continuous swap and turn it into a Zeno effect. And this is where Franson's proposal comes in 2004, where he imagined taking these fibers and putting them in an atomic cloud, where where the wavelength of the photons and interacts with the atoms in such a way that we have a very strong two-photon absorption. And what does this do? This means that if there's two photons in one fiber, they'll be absorbed by the atom cloud. Whereas if there's one photon in the fiber, this photon will be perfectly transmitted through the atom cloud. And this two-photon absorber is going to act like a measurement and prevent the photons from bunching into one mode, just like the Zeno effect prevents the atom from decaying. So what we need for this is some platform of strong two-photon absorption, but no single-photon absorption. So just to look at this in a bit more detail, what happens in general in one of these, if we take these two modes and we have a photon coming in each of the modes, the photons are going to start propagating through the modes. And now once we bring those two modes close together, we're going to get some coupling, and there's going to be some probability that the photons bunch and jump into the same fiber. But if this happens, that two-photon absorber is going to absorb the photons and kick them out. So we're not going to have, so the photons will be, they won't be in the fiber anymore. They'll be kicked out. And this is effectively a measurement. Because in principle, you could look at the state of the atomic cloud and tell whether or not the photons have been absorbed. So if we apply the logic from the Zeno gate, then if we have the strong two-photon absorber, it's actually going to prevent the system from bunching in the first place, and the photons will propagate. And any time they say try to bunch, the two-photon absorber is actually going to prevent them from bunching, and we'll end up with both photons emerging from the beam splitter, from this directional coupler, without having swapped. So it turns out that this can actually completely suppress the Hung-Amandel effect. But for this to work, we need strong two-photon absorption compared to the probability that the photons are going to bunch. So just a few more words on what the qubits look like in Franson's proposal. In Franson's proposal, we imagine encoding the photons in the following way. We just use the presence of the photon to be a logical one. So if there's one photon in mode A, this is a logical one. If there's no photons in mode A, this is a logical 0. So now the gate becomes almost trivial when we think about the state 0, 0, because if we send no photons into this mode, into these modes, no photons are going to exit in these modes. So this state holds. Now, if we send one photon down here, we've adjusted our length such that we have the root swap condition. So we end up with a probability of we end up with the photons exiting in an equal superposition of these two modes. The same thing happens when we send a single photon in the upper mode, except we pick up a negative phase, which does actually come if you work, which you can actually see if you work out the details. And then finally, the 1-1 state is a state that we really require the Zeno effect to save. So the 1-1 state, now the Zeno effect is going to prevent that from evolving, from bunching, and keep us in the 1-1 state. And this is exactly the root swap logic gates, which, remember, I guess you couldn't see this on my first slide, but hopefully you see it here. The controlled NOT gate is equal to 2 root swap gates. So these guys here are the root swap gates, and these other gates around are single qubit logic gates. So this is great, but how can we actually build it? So Franson proposed using atoms in optical fibers interacting with atom clouds, and they made some nice experimental progress towards this, but it kind of faces the same challenges that a lot of these other atomic experiments face. Namely, they're very difficult to integrate, and even building one copy of the gate is extremely challenging. So this is where we decided to start looking at this graphene plasmonic platform. So let me say a few words about the physics of this platform, because I think it may not be so familiar. So first off, what is a plasmon? So a plasmon, in particular, we're going to be focusing on something called surface plasmon polaritons, which I'm going to refer to as plasmon throughout this talk. So these are states where we have some material. So say this grayish area here is some metal, typically, and above we have air. What's important is that there's a change in the dielectric constant across this interface. But now if the light comes in, that light will interact with the atoms or with the electrons at the surface, and we can actually create a propagating wave solution where the light couples partially to the electrons in the surface, and then it's going to kind of sustain this traveling wave that can, re-emit light, and the electrons will kind of reorganize themselves to help this effect keep going. So we end up with this weird kind of excitation, which is traveling across the interface of this metal. One of the challenges of this system. All right, so this has many applications outside of quantum information. Actually, typically most of them are outside of quantum information. And one of the reasons is that the plasmons have a much smaller mode volume than light. You can think of this, now we have, we no longer have just a photon which has no mass, but we have some quasi-particle which is really made up of photons and electrons. So now these electrons from, say, 2 different plasmons are going to see each other much more strongly than 2 photons. So people have been using these sorts of systems to enhance nonlinearities, for example, by essentially confining the light and giving it some matter component. One of the big challenges with standard plasmonics, especially with respect to quantum information experiments, is that there's a very strong limit on how far you can propagate light or plasmons on a metal. And this is essentially because these electrons feel some resistance from the bulk, and this results in an exponential decay in the propagation length. So even though we have a traveling wave solution, there's an exponential envelope, so we're not actually going to propagate for very long. And this is in standard materials. Nonetheless, people have shown that you can use these metallic plasmons to do quantum experiments. There's a very nice paper from, I guess, 7 years ago now, where they showed that you can take 2 metal ribbons, so these are metal wires here, and they excite photons on this side. They send single photons into this and couple to a plasmon over here, and another single photon couples to a plasmon over here. The two modes are brought close together, just like in a directional coupler, and you can have essentially a 50-50 beam splitter for plasmons, and they observe that you can have a Hong-Emanuel effect even with metallic plasmons. So this brings us to graphene. It turns out graphene also supports plasmons, but what's interesting about the graphene platform is two things. Essentially, number one, it has a very large chi3. So it has a very strong nonlinearity per unit length. It's a single atomic layer. So, but it still nonetheless has a strong nonlinearity. And the plasmons are extremely long-lived compared to metallic plasmons. And what I'm showing up here in this top corner is an experiment from one of our collaborators from 2012, where they actually showed that they showed that you can create plasmons in this little island. So this this triangle here represents a triangle of graphene, and they send light into the graphene. They use some tricks to couple that light to plasmons, but they excite plasmons, and then they have other techniques to actually map out the plasmon interference pattern. So this is actual experimental data where the color bar represents essentially the intensity of the plasmonic field in this structure. And you can see you have like interference effects where the plasmons reflect off of the edges of this triangle and they actually interfere at the tip here. You can then take this further. This is a relatively large structure compared to the plasmon wavelength, but you can start to imagine now if instead of using a big triangle, we use a small nanoscale island of graphene, we can actually create resonant structures that are resonant to the plasmon wavelengths to enhance these sorts of nonlinearities even further. And there was and based on this effect, the Lukens group put out a proposal showing that you can use these little nano islands to actually create something known in standard optics, AMO, as the photon blockade, but you can do this now with plasmons. So they proposed using the plasmonic blockade effect in graphene islands to actually create a single photon source. I won't go into too many details, but essentially the rough idea is you send classical light into the system. You can excite a single plasmon, but if you try to send in a second photon, the plasmons in this island interact so strongly that they actually shift the resonant wavelength of the nanostructure. So the second photon won't be able to couple into the nanostructure. And then if you look at the emission of the nanostructure, you'll find that it's purely single photon. So you end up with a single photon source. So this takes us to our proposal. We decided to use this platform and see if we could use it to do the root swap gate. Because we have now a plasmonic material in which we can propagate plasmons for very long distances in the presence of a nonlinearity, this sounds like a good candidate for the Franzen Zeno gate. And essentially, it works quite well, it turns out. So what we imagine is we take some graphene ribbon, or really a ribbon made out of graphene, and we see what happens when you start to send single plasmons down the ribbon. And based on a very simple picture, if we tune the energy of the graphene, so this cone is the typical Dirac cones of the graphene band structure, we can tune the energy such that a single photon transition will not be allowed because the electrons are already there, but we can still have a two photon transition that will jump up above the band, and this transition can happen. So now we have single plasmon absorption forbidden, but two plasmon absorption allowed. And what I'm plotting here is something that we've calculated, which is the ratio of the two plasmon absorption to the one plasmon absorption. So if we want the Zeno gate to work, we need very high two plasmon absorption and very small one plasmon absorption. And what you can see is on this axis, we have the width of the nanoribbons. So we're considering ribbons from 5 nanometers to 25 nanometers in this plot. And over here, this is the energy level in the graphene. And we see that we have this band here where we have quite a high ratio. So we have like a 4 order of magnitude difference in this particular data or simulation for this ratio. So this really does seem like the perfect platform for Franzen's Zeno gate. And this is just a sketch more along the lines of what we imagine. It's fairly theoretical sketch. So in practice, this would maybe look a little different. but the physics you can kind of get from this. We really imagine having two nanoribbons, bringing them close together. And now, rather than having an evanescent coupling between the ribbons, we have a Coulomb interaction between the two ribbons, and that's going to allow us to implement a directional coupler, a beam splitter, and so on, and look at the root swap effect. So we model the system as follows. We create a mathematical description of the gate by considering a 6-level system. And what's shown in this picture up here is an energy diagram where here we have ribbon, this state here represents the ribbon on the left and the ribbon on the right, but with no plasmon in either mode. This is the ribbon on the left with a plasmon in one mode and nothing in the ribbon on the right, the opposite for here. And here we have the plasmons with one ribbon in each mode. And here we have the states where the two plasmons have bunched together into the same mode. And then, of course, we can go between these modes with various couplings. So to go from, say, from this mode to this mode, so we have a single plasmon swap its state from the left to the right. We look at the Coulomb interaction, the Coulomb coupling between these two ribbons. And then we also need the various decay rates. So the single plasmon decay rate can let us decay from this state to this state. And the two plasmon decay rate will take us directly down from two plasmons in one wire all the way down to the ground state, essentially, with no plasmons. And then we create a master equation, a Hamiltonian, and we can create use the master equation to solve the problem and see what happens under various circumstances. So to calculate all of these things, we used, we're not plasmonic experts, so we had help from the theory group of Javier Garcia de Abajo from ICFO in Spain. And they showed us how we could actually calculate these coupling strengths directly. So the coupling between the ribbons and the two plasmon absorption between the ribbons, which the form of these expressions doesn't matter too much, but we can now use them to model this system. So we take a very simple situation where, for example, we have one plasmon coming in the upper mode, and we want to figure out how long it's going to take to evolve to a situation where we have one plasmon in each of the output modes. So we simply set our initial conditions such that we have a single plasmon here, and we solve the equations and look for the time at which the probability of the photon to be in mode A is equal to the probability of the plasmon to be in mode B. And now we just want to see how long this is going to take and compare that to the typical plasmon lifetimes. So what's plotted here is, again, on the x-axis, we again have the nanoribbon width, and on the y-axis, we have the energy levels of the energy in the graphene. And the color bar now represents the length at which the plasmon will swap with 50% probability. So in this case, we want the plasmons to swap relatively quickly because we want the swap process to occur fast enough before the plasmon decays. So typically in graphene, you can have these plasmons propagating something like 500 nanometers to a micron without too much loss. So we want something below 500 nanometers, and you can see we have a wide range of parameters for which this works. So now what we can do is see if we can actually use this system to implement the Zeno effect. So we're now going to model a situation where we have one plasmon coming in on mode A and one plasmon coming in on mode B. Now we're going to let it evolve for the length we just calculated on the previous slide and see what happens. We're going to look at first the probability that both photons end up in different modes. So this is the probability of finding a coincidence, essentially. And again, plotting versus ribbon width and energy, we see that we have this white band here where we have a fairly high probability that the plasmons are going to stay in their own ribbons. And in this case, for these parameters, we found a success probability of about 80%. And we can look at some of these other regions and some of these other states to see what happens. For example, in this upper corner here, where we have a very weak two plasmon absorption, if we look at the 2,0 and the 0,2 terms, we now see that these are actually fairly large. So we have a high probability now of finding the plasmons to be in either of the modes 2,0 or 0,2, which is exactly the plasmonic Hong-Mandel effect. So this region here corresponds to, the Hong-Mandel dip for plasmons. So to go into a bit more detail, we also looked at simulating process tomography on the gate, and we find that with reasonable parameters, we find a process fidelity of about 93%. So we have a 93% process fidelity if we assume a kind of standard plasmon lifetime at room temperature. You can improve the plasmon lifetime by actually cooling the graphene down to, say, liquid nitrogen temperatures. And now what I'm plotting here is the success probability, so the probability that we keep the photons in the 1-1 state versus the lifetime of the plasmons. And we see that as the plasmon lifetime gets better, obviously the gate performance improves. And for plasmon lifetimes above about 7 picoseconds, we have success probabilities above 99%. And I should mention that people have observed already about 10 picosecond lifetimes in graphene plasmons at cryogenic temperatures. So this is something that we think could actually be useful for implementing some of these nonlinear effects. Of course, there's a bunch of assumptions in our model. We use a very simple single mode treatment of the model. So, we would, in practice, to implement, before setting up an experiment to implement this, we need to come up with a more realistic model. And one of the big things I didn't touch on at all is coupling from free space to the graphene plasmons. So free space coupling to plasmons is typically challenging because there's a very large mode mismatch. And in our proposal, we didn't particularly address this, but I should mention that people in the field are working on different ways of coupling light to plasmons efficiently. But in any case, it does show that this is a device that has a footprint of a few tens of nanometers, and it lets us reach single photon level nonlinearity. So we think this is a very exciting platform and something that is worth pursuing. So how am I doing for time?
I think I still have about 10 minutes, I guess. Yeah.
10 minutes? Okay. Okay,
yeah.
Great. So then for the next 10 minutes, I'll go over kind of what we've been working on in the lab. So what I showed you so far was just an experimental proposal. But we have been making steps towards this in the lab, albeit in a slightly different system. So what we've done, just to summarize, is we've looked for a plasmonic effect on a nonlinear signal, and we found that we were able to look at third harmonic generation in a graphene nanostructure and show that the plasmons are actually mediating the nonlinear process. So what do our samples look like? Unfortunately, the graphene manufacturing technology still hasn't caught up to what we want to do. So for our proposal, we said we want nano ribbons, graphene ribbons that are about 10 nanometers wide. And this is something that's very challenging to do in practice. So what we're going to do instead is we're going to take a big sheet of graphene, and instead of patterning the graphene directly, we're going to put metal nanostructures on top of the graphene. So this is, say, now a cross section of one of our samples where we have a graphene layer, some spacer layer, and then a metal ribbon on top. And if we look at what happens if we simulate what happens when we shine light on this ribbon, we find that we can excite plasmons in the graphene layer, which is represented by this dashed line, but they don't actually extend into the metal. So all of the field, this is now the electric field of the graphene plasmon, lives under the metal. And the edges of this metal nanoribbon actually set a boundary condition. So the plasmon, it could reflect off of these edges and form a standing wave underneath the metal. So we can make these sorts of resonant structures. So we can make these sorts of resonant structures with these metal nanoribbons. And because the electric field doesn't extend into the metal, we don't have the limitation of metal plasmonics. The other simplification we're going to do is, instead of using a single ribbon, we're going to use array of ribbons. And this is an SEM scanning electron microscope image of one of our samples. It's not too exciting, but these grayish areas here are the metal nanoribbons on top of the graphene layer. And these devices were originally made by Frank Koppen's group in ICFO. And what they showed is that you can actually create plasmons in these structures, and you can have these resonant modes underneath the metal. One of the challenges is that in these devices, the plasmon resonances occur at very long wavelengths. So this axis here is in wave numbers, and I guess this peak is probably actually longer than 6,000 nanometers. I think that's from a different sample, but this is like 7-8 microns where we see this peak. So these are transmission measurements through one of these structures, and this peak here corresponds to the excitation of the plasmon. But now we have long wavelengths we have to deal with. So what we're going to do to kind of get around this experimentally is we're going to use third harmonic generation, which is going to let us probe these effects. So we're going to come in with light at omega and look for emission at 3 omega. So in practice for us, that means if we come in with light that has a wavelength of about 6,000 nanometers, we're going to generate light at about 2,000 nanometers. And this is good because 2,000 nanometers is now light we can detect using our single photon detectors, which are designed to work at 1550, but they still have some finite detection efficiency at 2,000 nanometers. So looking in a bit more detail, what happens on these structures? Well, we come in with light, and what we actually initially do is we create metallic plasmons in these ribbons. And when we do that, we actually have kind of an antenna-like effect where we get this big field enhancement on the edge of the ribbon. And this field enhancement is we're going to use this field enhancement to actually couple the free space light into the graphene plasmon mode. And it's also, as a nice side effect, it's going to intensify the light in the graphene layer, which is going to just give us this effectively stronger intensity and allow us to see the nonlinear effects more easily. So what our experiment looks like, a very simplified sketch of our experiment is shown here. So we take a long wavelength beam, in this case 5,500 nanometers. We just have some optics to control the polarization, and then a lens to focus down into our graphene sample. And then we have another lens to collimate, and we couple to fiber and send it to one of our single photon detectors. And we're going to look for light at about 1,833 nanometers in this case. We can also tune this wavelength and kind of see what happens at different wavelengths. And then we're going to use filters to filter out the pump light. And we can also measure the spectrum to make sure that we're really looking at third harmonic generation. So most of our experiments proceed as follows. We simply take our sample and we translate it through the focus. So, when the sample is here at the focus, we expect a maximum in the signal. When the sample is far away from the focus, we expect a much smaller signal because the intensity of light is smaller. And this is what we see. So what's plotted here is the third harmonic power plotted versus the Z position in the experiment. So when we're at the focus, we see a peak. And these different curves correspond to different places on the sample. So, we've done control experiments to make sure we have no signal unless there's graphene present. This little red bump here is a signal from just graphene on its own. And this big blue bump is the enhanced signal when we have both graphene and the metal nanostructure to enhance the signal. And notice that this is also logarithmic scale. So we have, in this case, we have an enhancement of almost 2 orders of magnitude. So we can go look into a bit more detail to try to see how much our nanostructures are actually enhancing the nonlinearity. Here we have, what I'm plotting here is a third harmonic power versus the pump power. And if we have a third order signal, we expect a cubic dependence on the pump power. And these lines are fits to the data which predict this third order dependence. And we have a fairly good agreement with what we expect. And the different colors up here are from ribbons of different widths. And this red curve down here is what we expect for, or is what we measure and for the graphene. And we can see for our largest, for our best ribbon sample, we have an enhancement of about 3 orders of magnitude on the third harmonic generation. We can also look at other nonlinearities in the system. We've also looked at fifth harmonic generation, which shows an even stronger enhancement of about 4,000 times enhancement between the graphene signal and the nanoribbon signal. Here I'm just showing we can also measure the spectrum, and we verify that our signals are actually third harmonic and fifth harmonic generation. So finally, how do we prove that there are plasmons, or how do we show that there are plasmons in our system? Well, what we do is we start to look at how the system responds when we change the energy in the graphene, as we tune the gating or the Fermi energy in the graphene. So when we tune the energy levels such that we're resonant to a 3-photon transition, remember we're taking 3 input pump photons and creating 1 photon at 3 omega energy. So when this energy level is resonant to the 3-photon transition, we expect the largest enhancement. And this is indeed what we see. So plotted down here is the third harmonic signal versus the graphene energy now, the Fermi energy in the graphene, for different pump wavelengths. So for 4,500 nanometers, for 5,000 nanometers, and for 5,500 nanometers. And we see in all cases the largest signal at the 3-photon transition. But for the longer wavelength data, we see an additional interesting effect in our experiment, which is this dip. And we've confirmed through some simulations that this dip corresponds to the excitation of a plasmon underneath the metal. So the way that we do that is we have this model of our experiment, and we can tune the parameters in our model, and we can show that this yellow curve here, for example, is what happens when we essentially turn the plasmons off. So if we make the plasmon lifetime, the electron lifetime, very, very short, we expect to see no features in our system. So that would be this yellow curve. And I don't have the data in this presentation, but that is essentially what we see when we measure planar graphene with no nanostructures. But when we improve the plasmon lifetime, we start to see much sharper peaks and this dip here. And this dip this dip in this red curve here is the same dip that we saw in the theory plot on the previous slide. So what's happening at this dip? Well, what I'm plotting here is the electric field we expect underneath the gold and then in the gap versus the photon energy. So versus the plasmon energy. Sorry, the Fermi energy in the graphene. So as we tune the Fermi energy in the graphene, we can see the field that we excite changes. And right here is at this location of this dip at about 3.5 photon energies. And this is for the conditions that we expect to see in our experiment. And we see that in this case, we do have this mode, which appears to be a standing wave underneath the gold. And we can see that when we improve the plasmon lifetime in our model, at least, we see even stronger plasmonic modes, confirming, although it's not really conclusive evidence, we need to do further tests to really see a clear plasmonic enhancement. But it is fairly strong evidence that we are exciting plasmons underneath the system, or underneath the nanoribbons in this system. So with that, I think I will, end. And just a quick summary, we showed in the first part of the slide, I showed you that we have this proposal for implementing logic gates using graphene plasmonic devices. And then I showed you our first steps to the experiment, which are maybe quite far from our ideal gate, but it's a first step. There's actually been very little work on doing these sorts of nonlinearities in graphene plasmonics. So this is a first step this was a first step for us to show that we have nonlinear effects mediated by graphene plasmons. We're also in the process of measuring other nonlinearities. We're currently looking into doing four-wave mixing. And we're looking to see, in particular, if we can see spontaneous four-wave mixing from a single atomic layer. In parallel, we're working at extending the detection wave of our single photon detectors to even longer wavelengths, as this will hopefully allow us to, really see these sort of single plasmon level effects. And we, one day we're still working to pushing to the single nanostructure regime. So with that, I'll just thank everyone who was involved for this work. Philip Walter, we did these experiments, in his labs, and we worked very closely together on all of this. And then in particular, the graphene team here in Vienna Ira, the PhD student, she's now a postdoc in the group who really kind of built the experiment up from scratch with me from the start. Alessandro Trenti, a postdoc who's been helping us, and then Philip Yanka, who's Ira's replacement, and then Hlib, who's our master's student. And then, of course, our external collaborators, the ICFO group, whom we get samples from and who help us understand what we're doing. The theorist, Javier Garcia de Bajo, and then yeah, the Henry group from the University of Exeter has also been useful for a bunch of these nonlinear measurements. And then, of course, the funding agencies. But with that, thank you for your attention. Yeah.
Sorry, I still, yeah, I was still turning on the camera. It took a few seconds. So thank you very much. So let's see if we have some questions. How do you see it? Probably comes by the chat or something else. So I don't know, but oh yes, shared notes. Oh yeah, okay. So there's a question here from Nara. Is just to let you know that Nara is from our group, is a postdoc. So she's saying, yeah, can you see this note? So I'll read for you. So she's thanking for the talk. The question is related to the coupling between light and SPPs,
yeah,
which you mentioned to be not an easy task. I suppose the point is to use the graphene-based gate for the logic operations, but still employ light for the transport of the qubits, right? Yeah. So how one get the photonic qubit after the graphene-based gate? And you have shown how the SPPs are created by light, but how does the inverse effect work? Get light from the plasmons. So,
yes, so you can use essentially to get the light. Well, so I guess first off, there's kind of two ways we imagine using the gate, and it kind of depends how technology improves. You could imagine doing everything at the plasmon level. And people have looked at coupling single photon emitters like quantum dots and NV centers directly to metallic nanostructures. And there have been proposals that you can also do this in using graphene plasmonics. So in that case, you would never really have a free space photon. You would have like a photon being emitted from like a single structure and then coupling directly to the plasmonic mode. So that's one way you could get around that. But I think honestly, that's, you know, needs a bit more work to really see happen. The other thing is, and people have done this in, actually, let me pull up a slide here. So people have done this in these metallic nanostructures already. So you can couple to the SPPs using, I guess you can't see it so well on this picture here. But yeah, actually, no, you can't see it on this picture, but you can use essentially a grading coupler. So you have like, so on the surface, you have, let's see. So say this hand is the plasmonic mode, and we want to shine light into the plasmonic mode and have it propagate along the surface of the nanoribbon, metal or graphene. What you can do is actually create a diffraction grating on, or something like a diffraction grating on the surface. So you have like little metal ribbons here, so the light can shine in, and you get a momentum kick from the grating, which allows you to couple to the ribbons. And now you can propagate as an SPP along the ribbon, and you have another grating at the other end where you want to outcouple. So the light can convert to a plasmon, propagate, and then convert back into free space. This is what people typically do in metal with metal plasmonics. With graphene, the situation is more difficult because there's an even larger momentum mismatch that you have to overcome. But if you solve it on one side, you do essentially solve it on the other side. So yeah, short answer, it's a very difficult it's still a very difficult problem, and there's not a clear solution yet. But
Okay, let's see. She's thinking. Well, let me ask you a question while other people may have questions. So, very exciting approach, and I would have many questions. I'll try to synthesize in more general, in a more general vision. So it seems that when you're trying to implement these logic gates, it seems to me that the idea is that you convert light to plasmons, and then the plasmons interact, and then from this interaction you can have the logic operation, and then you convert back to light. Is that correct? So, but when you create the plasmons, you need too many photons, or can you create a plasma from single photons?
You can create a plasma. You can actually create a plasmon from a single photon. So the conversion of light to plasmon isn't a nonlinear effect. So it's lossy, but it's not nonlinear. So if you can do it for classical light, then in theory you can also do it for single photons. And this is my screen. My screen is gone now.
Yeah, your screen is not being shared anymore.
Okay. Yeah. So but people have done this with single photons in metal plasmonic structures. So there's several experiments that have shown you can take a photon, convert it to a metal plasmon, and then get it out on the other side, even like with a down converted photon.
But I mean, in your proposal of implementing the root swap gate, do you need to start and end up with single photons, or can you use light pulses, for instance? So
you would need to start with single photons, because if you start with coherent states, yeah, it wouldn't be you wouldn't stay in like the computational basis. It's really important for the way we encode the photons that you have either 0 or 1 photons. If you have a coherent state, then there's some probability that you have 2 photons, which should be a failure mode. So so it wouldn't work. I mean, the gate would do something. There would be some sort of interference in it, but I guess it would be similar to, say, taking like a bulk controlled NOT gate, a Hong-Mandel based controlled NOT gate, and sending in coherent states to that gate.
I see. So, and I have another question is concerning the nonlinear interaction. So, when you use this polaritons as a nonlinear medium, so it seems to me, it feels like the plasmonic excitation plays the same role as the polarization in a dielectric medium. So the electric field polarization. So, but the difference is that when you create the polarization in a nonlinear medium, for instance, Chi2 polarization, something like this, so it stands still because it does not propagate that. But then the polaritons is a nonlinear polarization that propagates through the medium. Is it a good idea of the process?
Yeah, so you create a propagating polarization, and in general for these polaritons it doesn't have to be nonlinear. In graphene there is a nonlinear susceptibility, so you will see nonlinear effects. But in general, for a plasmon, you don't need a nonlinear propagating solution. But yeah, you do essentially have this propagating polarization in the dielectric, or sorry, in the metal in this case. But it has to be at the interface of the dielectric and the metal.
So, but then you have demonstrated up conversion, okay? But because
experimentally, you mean?
So no, yeah, I understand your motivation, but I mean, you have demonstrated the up conversion of light. So could you have down conversion like in dielectric medium and the spontaneous emissions?
Yeah, you could, and this is something we're actually currently trying to do. So you can have, I mean, so it's not exactly down conversion because it's a chi-3 nonlinearity rather than chi-2, but it would be spontaneous four-wave mixing. And we've observed classical four-wave mixing in graphene in the past, and we're currently we're setting that experiment up again right now, and we think we can kind of get to the regime to actually see spontaneous four-wave mixing. Yeah, and that's interesting for a few reasons. It's not really going to compete with like a down conversion crystal, for example, because with graphene you have a single atomic layer. So you have, you know, a third of an angstrom thick crystal, essentially. So to really compete with the down conversion stuff, you need to get to this nonlinear nanostructure regime. But what is interesting is when you start doing nonlinear optics in a single atomic layer, the physics is a little different because you don't have phase matching, for example. You have a single atomic layer, so there's no way for the phase to build up or anything. So phase matching considerations don't play a role. So you can think about doing things like generating light at one frequency, or photons at one frequency and another photon at a very different frequency because there's no phase matching constraints.
Okay. Very nice. So let's see. Are there other questions? Let me check. There is another question. Don't know from who, but are there logic gates other than the root swap implemented with graphene plasmonics?
I'm not aware of any. So the only other quantum proposal I'm aware of in graphene plasmonics is it's a proposal from Misha Lukin's group to use it for a single photon source. So it uses similar effects where now instead of a ribbon, you have a single island of graphene, and you look at it. You look at the emission from that island of graphene, and it's a single photon source. But as far as I'm aware, no one has proposed another logic gate in graphene.
Okay. There are questions. No, not. There are not questions in YouTube. All right. So I think we can stop. Okay. Because it's almost time for lunch here. Anyway. Yeah. So thank you very much again. So I hope we can meet again in person, whether in Vienna or in Floripa. We are waiting for your visit here, Floripa. It's sunny today, so I hope you can come here in a sunny season, so you can go to see one of the 44 beaches of Floripa, at least. Yeah. Okay. So I think I will finish. So thank you very much. See you.
Okay.
Guilherme. Bye-bye.
Bye-bye.
Ciao, ciao.
Ciao.